In the last screencast, I mentioned that the next thing we were going to talk about were E1 reactions, but I realized that I'd rather go ahead and talk about the stereochemistry of E2 reactions a little bit more before we jump into E1 reactions. So the transition state of an E2 reaction consists of 4 atoms from the alkyl halide. And we've looked at this before. And the 4 atoms from the alkyl halide are, and I think I'm gonna highlight them here in blue, right? Are 1 hydrogen atom there. We've got 2 carbon atoms here, right? And then the leaving group here. Now, all of those are aligned in a plane. That means that if we had a piece of paper sitting down, these would all be next to each other, right? Now these may be sticking up or back, but these are all going to be flat with a piece of paper, okay? So they're all lying there in a plane. Now, there are 2 ways for this carbon-hydrogen and carbon-halogen bond to be coplanar. Now, when we're all aligned in a plane like this, right, and we're talking about 2 ways for the carbon-hydrogen and carbon-halogen to be aligned in a plane, right, that is called coplanar. Okay, where both of those, this one and this one, are aligned in a plane to each other. Now, when we look at those 2 ways, right, one way is that the hydrogen and the halogen can be oriented on the same side of the molecule, and that geometry is called syn-periplanar. So the H, the hydrogen, and the halogen are aligned on the same side of the molecule, right? Then you can also have an orientation where the hydrogen and the halogen are aligned on opposite sides of the molecule. Right? So when we look at this, one is here and one is here, and those are on the opposite sides, but it's all still flat. And this is called anti-periplanar. Now, evidence suggests that E2 elimination reactions occur most often in the anti-periplanar geometry. So, what we find is that this arrangement allows for the molecule to react in the lower energy staggered conformation and allows the incoming base and the leaving group to be further away from each other, okay? So this allows the incoming base and the leaving group to be further away from each other, okay? And so if we, by comparison, look at the syn-periplanar arrangement, here they're eclipsed. And so because they're right here and eclipsed, they're pretty close to each other, and when the base comes in, that's in a position that's pretty close to that halogen as well. And so that base has a lot of negative charge, the halogen has a lot of negative charge. They're just really too close for that to be super favorable. So by keeping these farther apart, right, that molecule, this is a more preferred favorable geometry. So what we find is this is the preferred geometry for any alkyl halide undergoing E2 elimination, whether it's cyclic or acyclic. And so I want us to look at a cyclic example. So we come over here to look at a cyclic example, right? And I want us to look at cyclohexane here. Now, cyclohexane exists as two chair conformers, and we've already talked about that. And we've already said, hey, look, the conformer here, where chlorine is in the equatorial position, is more stable because that bulkier group has more room. And it will go through an equilibrium where chlorine will go into the axial position, but in the axial position, it has more interactions with hydrogens that are also axial. And so that's just a less stable position due to steric hindrance. Now, for an E2 elimination, the carbon-chlorine bond must be anti-periplanar to the carbon-hydrogen bond on the beta carbon, which is shown here in blue. And then this other beta carbon is also, if it's going to be removed, needs to be anti-periplanar. Now, this only occurs when the hydrogen here and the chlorine here are both in the axial position. So this is the conformation that reacts in an E2 reaction. This a lot of times is referred to as trans diaxial, right? Where the diaxial refers to chlorine being in the axial position and the hydrogen here being in the axial position. And so that means for an E2 reaction to occur with a molecule in a ring, it needs to occur with the conformation that's less stable to give us this ring. Now, let's look at an example. So consider cis and trans 1-chloro-2-methyl cyclohexane. Okay, when we look at this, right, the cis isomer. So we're gonna zoom into the cis isomer, and we're gonna come back to the trans in a second. But let's just look at cis for a moment. The cis isomer exists as two conformations, A conformation here and B conformation here, each of which has one group axial and one group equatorial, right? And the E2 reaction must occur from the conformation B, where you have the axial chlorine and then the axial hydrogen here, okay? So we've got to be here in conformation B. Now, because conformation B, which we looked at, has two different axial hydrogens, beta hydrogens, labeled HA and HB, right? So remember, this is the alpha, there's the beta, and there's the beta. And so we have two different ones here and here. The E2 reaction occurs in two different directions. And so in one of these, HA is removed to form this product, and in the other one, HB is removed to form this product. Now, the major product, or the one that we get the most when we do this reaction, is this tri-substituted alkene, right? And that's predicted by Zatsev's rule. Okay, and so maybe the burning question in your heart is, what about the trans isomer? Does it also follow Zatsev's rule? Well, when we look at the trans isomer, right, it exists, right, as two conformers. One where you have two equatorial substituents, right, and then one where you have two axial substituents. Now, this is the conformation that reacts because it's the one that contains the axial chlorine. So the big take-home message here is that for the conformation to react, the halogen must be in the axial position. Right? So, when we look at this, right, this particular molecule only has one beta axial hydrogen to react. And so it's shown right here in red. And so it's the one that reacts. And, you know, because it's the one that is axial on a beta carbon. This one is equatorial. So it's going to have to react with this one. And what happens here is we get a di-substituted alkene only product. Now, this doesn't follow Zatsev's rule, right? Where the most substituted alkene is the major product in this case. Because if we were to remove this one, right, that would give us a more substituted alkene. Right? But it doesn't occur because the hydrogen is not axial. Right? And so because of that, we get the anti-Zatsev's product here. And an anti-Zatsev's product just means that it's one that doesn't follow Zatsev's rule, right? Where we get the di-substituted alkene instead of an alkene with a double bond. So if we were to remove that one, we would end up with an alkene that had a double bond there and would be tri-substituted. But because this isn't axial, that doesn't occur. So now in the next screencast, you're going to learn about E1 reactions. As always, if you have any questions, please feel free to pop by my office.